Hi, this is Dr. Nick with the last section in Chapter 6. We're going to practice measuring intervals. Well, here's the next one. If you look at the forest, it looks pretty regular. And if you look at the R intervals, it looks like it's falling one small box behind the heavy line. But look at that. It's sort of consistent. Every beat is on the same relative location. So what would the rate be? Well, start with this one. We'll count off 300, 150, 100. So the rate here is 100 beats per minute. Okay, let's look at the PR interval. This PR happens to land on a heavy line. The QRS lands right over here. So that's 3 small boxes. That's a relatively short PR of 120 milliseconds. Now, what is the normal PR interval? That's what we'd like to know. So the normal PR interval is 120 to 200 milliseconds. The normal QRS should be anywhere from 80 to about 120 milliseconds. And the normal QT interval, well, there isn't one, but the QTC should be less than 420 in men and 440 in women. Okay? So 120 fits into the normal range, but keep in mind this is a young patient. The heart's going fast, so their AV conduction kind of gets enhanced that way. The QRS starts with this light line and ends right about here. So you'd call it 40, 80, and not quite a whole nother box, so that's another 20 milliseconds. That gives you 100. So 100 milliseconds for the QRS duration, that's in the normal range. And then for the QT, we're going to count from here, 40, 80, 120, 150, 200, 40, 80, 120. And it comes down to the baseline here, which is another 40, 160, about 180 milliseconds. Add that to the 200, and you get 380 milliseconds. Now, was that a normal QT? Well, it might be. If we look at the midpoint between the two R to R intervals, we're going to wind up being about here. And that's right about where the T wave ends, isn't it? So now let's plug it into our formula. It's actually called Bazet's formula. So the QTC is equal to the QT times 1 over the square root of the R to R in seconds. If you want to do it a different way, you can rewrite it as simply the QT over the square root of the R to R interval. So if the R to R interval is 600 here, because it's 3 heavy boxes, that's how many seconds? 0.6 seconds. That's 600 milliseconds. If this is 600, you bring the decimal point back to the left 3 spaces, 1, 2, 3, and you get 0.6. So let's bring our calculator in here. We'll say 0.6, the square root of that. 1 over the square root is 1.29, and multiply that times the QT that we measured, which was 380, and we get 490. So lo and behold, this QTC is a little bit on the long side. If this was a woman, you'd be a little bit concerned. If it was a man, you'd be especially concerned. So what we found here is a fairly short PR, a normal QRS duration, and a QT interval that, when corrected, looks to be a little bit long for this patient. Okay, one last example. This one's a little bit harder because the QRS and the P wave is sort of small, and it's kind of hard to measure. But let's do it really quickly. Now, here's a QRS that's very close to the heavy line. So let's count off 300, 150, 100. This would be 75. It's closer to 175. It's probably something along about 85 beats per minute. If you want to measure an exact interval, we can count 200, 400, 600, and then another 60, because that's 1.5 small boxes. So that's 660 milliseconds. If somebody wants to take out a calculator and divide this into 60,000, you'll get exactly the rate. Let's leave that as a homework assignment, shall we? Okay, so there's the rate, there's your interval. The problem is it's hard to see exactly where the P wave starts. So you kind of have to look at a couple of beats and get a better sense. That's where calipers can become very helpful. So I've already taken this pair of calipers and set it for what I think is the beginning of the P wave and the beginning of the QRS complex. And lo and behold, if you move it along, you can see that it's fairly consistent. So now let's put the point on a heavy line, and we can see it's just a hair over 200 milliseconds. Maybe it's not even, maybe it's exactly 200 if you want to call it that. So here our PR interval is 200 milliseconds. So that's kind of at the upper limits of normal. Our QRS duration is from here to here, so that's about 80 milliseconds, and it looks pretty consistent. And the QT we'll have to measure. And here again, we don't have a QRS complex that lands on a heavy line. So that's, again, where calipers become important. Okay, so here they are. And we're going to drag them over so that the 1 point is in the beginning of the QRS complex. And then we will stretch them out to the end of the T wave. And then we can pick up our points and place the 1 point on a heavy line. And we can, lo and behold, measure about 350 milliseconds. Got that? Because it would be 400 if it was two big boxes. 400 minus 40 and then another 10. So 350. All right, so we'll get rid of our calipers and then calculate the QTC. So remember, the QTC is equal to the QT over the square root of the R to R in seconds. We have 660 milliseconds, so that comes out to 0.66 seconds. So we take the R to R in seconds, which is 0.66. Take the square root of that, 1 over that number, times the QTC that we measured, which we said was 350 milliseconds, and that gives you 430, which is pretty normal. All right, so now that was kind of a long discussion, but I hope you get the idea. Measure the R to R interval so that you can calculate the rate, then look for the PR interval, the QRS duration, the QT, and then, of course, correct the QT for the rate by using Bazette's formula. And there you have it. Now, when we talk about AV node conduction, we'll be able to define things like first-degree AV block, which is present when you have a PR interval of greater than 200 milliseconds. But that's a topic for another video, isn't it? Anyway, for now, this is Dr. Nick for the ECG Academy. Thanks for watching.